All right, here we are with example 5 in the packet for the principle of mathematical induction. So far in the first 3 examples, we stuck with strategy 1. In example 4, we looked at strategy 3. Now we're going to use strategy 2 for example 5. We're not going to make an equation or anything. We're just going to continue the pattern for one more and figure out and to make sure that it's true. So, in example 5, we are proving by induction that 2 to the n power is always going to be greater than n for all positive integers of n. First, again, we have to show that it's true in the first case. So when n equals 1, we can just sub a 1 in for my n there and there. 2 to the first power is 2. 1 sub in 1 for n is just 1. So 2 is bigger than 1. Check. Next, my assumption stage, I'm going to assume that 2 to the k power is greater than k for all positive integers k. Again, it's just changing the exact statement, changing all the n's in the statement to k's. Next, we're going to be using strategy 2. In this case, you can run it 2 different directions. You can either do one more k and make it a k plus 1 and then argue until it's true, or you can start with what you already know and do the algebra until you get it to have a k plus 1 still true. So I'm going to do it that way. Starting with what I know, 2 to the k is greater than k. Right? I am allowed to multiply both sides by 2. Right? Multiply 2 on this side, multiply by 2 on that side. The bigger side is still going to be bigger. 2 times 2 to the k. Well, when I multiply things that have common bases, this exponent here is a 1, so I can add exponents. Those are our exponent rules. So my new exponent there is going to be a k plus 1. On the right-hand side, I just have a 2k. Right? So far, my left-hand side is now looking like what I want it to have a k plus 1 in place of what used to be a k. Now I just have to get the right-hand side to have a k plus 1 on the right instead of this 2k, which sounds very difficult, and it would be if this was an equal sign. But this actually becomes a much easier question because it's an inequality. All I need is the right-hand side to be less than the left-hand side. So 2k is equal to k plus k, right? That's just addition. Right. What I'm going to do, though, is I'm going to introduce this extra term extra part of the inequality on the right. Do you agree that k plus 1 is always going to be less than or equal to k plus k? Right? K at the first part is still k, but this k here has to be bigger than or equal to this 1. Is it always? Yes, it was because of our assumptions, right? So this far right-hand side has to be either smaller than or equal to the middle, which is still going to be always smaller than my 2 to the k plus 1 power. So because this is even more or less than this, I can just drop out this middle part and say that 2 to the k plus 1 is still bigger than k plus 1. Always. Notice now my k, where I used to have a k in the exponent here, is now a k plus 1. Where I used to have just a k off on the right is a k plus 1. So I have everything replaced with k plus 1s. So k plus 1 equals n, just like n equaled k originally. So it's true for both n equals k and n equals k plus 1, which means I can end it by the principle of mathematical induction. 2 to the n power is greater than n for all positive integers.